Welcome to episode 84 of the Energy Balance Podcast, where we teach you how to live without constant hunger and cravings, fatigue, brain fog, poor sleep, and other low energy symptoms by maximizing your cellular energy. I'm Jay Feldman. I'm a health coach and independent health researcher, and joining me again today is my good friend Mike Fave. Mike and I have been studying health and nutrition for a long time together, and Mike also draws on his experiences from working within the healthcare industry. Today's episode will be part one of a two-part series discussing whether David Perlmutter and Rick Johnson are right about fructose and uric acid, and whether their view means that we should be avoiding fructose. And of course, I do want to mention here that this is not personal at all toward Rick Johnson and David Perlmutter, and we'll be digging a lot into the physiology and biochemistry throughout this series, but we'll try to be breaking it down into simple terms so that it's easy to understand. And we'll be including some graphics and diagrams if you're watching on YouTube. So in this episode, we'll be talking about whether David Perlmutter and Rick Johnson are right about fructose and uric acid being drivers of poor metabolic health. And this is, of course, why we're bringing this episode up or doing the series, because what they're basically saying is that fructose, and we'll dig into this, but fructose will increase uric acid production, and this is the main reason why fructose is an issue. So we have in previous episodes discussed why the idea that fructose drives de novo lipogenesis and fat production in the liver is not really the reality and is not reason to avoid fructose. And so we'll be diving into this new argument today, which is kind of the biggest anti-fructose crusade at the moment. And so more specifically, we'll be talking about why fructose will not cause ATP depletion when it's consumed in normal contexts. We'll be talking about why fructose and uric acid are not the drivers of metabolic syndrome and degenerative conditions. We'll be talking about the protective effects of fructose in the liver and why it's extremely important to consider the different contexts in which uric acid is produced. If you are new to this podcast, I'd highly recommend you go back and listen through episodes 1 through 7 after listening through the series to help build a foundation and understanding of the bioenergetic view of health and nutrition. To check out the show notes for today's episode, including all of the links to the studies and articles and anything else that we discuss, head over to jfeldmanwellness.com/podcast. And if you are dealing with any low energy symptoms that you're trying to resolve, maybe those are related to concerns related to fructose, and those could be symptoms like low energy or fatigue or cravings and hunger, joint pain, weight gain, digestive symptoms, brain fog, poor sleep, hormonal imbalances, or various other low energy symptoms or chronic health issues. Again, maybe those are related to insulin resistance and diabetes, or gout, as we'll be discussing today, or heart issues, or autoimmune conditions, or anything else along those lines. So if you are dealing with any of those issues or symptoms, then head over to jfeldmanwellness.com/energy, where you can sign up for a free energy balance mini course, where I'll explain how these different symptoms and conditions are really caused by lack of energy. And I'll also walk you through the main things that you can do from a diet and lifestyle perspective to maximize your cellular energy and resolve these symptoms and conditions. So to sign up for that free energy balance mini course, head over to jfeldmanwellness.com/energy. And with that, let's get started. All right, so I've gotten a handful of questions on this topic. I'll share one in a second, but there's a new anti-fructose crusade over the last couple of years that's mostly been started or put forth by Rick Johnson and David Perlmutter. And they're discussing how fructose increases uric acid and that is the current main reason why we should all be avoiding fructose and why it is responsible for basically everything bad that can happen to our health. And they've been doing the rounds on podcasts and each have books out and everything on this thesis. And Rick Johnson also has some studies and everything. So we're going to be breaking all that down. The question I got, I'll just share one of them from Francois, who said, I heard Dr. David Perlmutter say he has a book coming on how uric acid should be at the center of the conversation for metabolic syndrome. He seems to accuse fructose and other high-purine foods. Any thoughts? And I've gotten a couple of similar questions, especially since that book has come out and seen this topic come up in the pro-metabolic bioenergetic world, the repeat forums and or forum and Facebook groups and all that. So figured it was worth digging into to kind of dispel some of the myths here, so to speak. And a lot of this really parallels what we discussed in terms of de novo lipogenesis and fructose, and especially the ideas put forth by Robert Lustig with his thesis that sugar and specifically fructose is a poison. And we broke all that down, especially in our fatty liver series. So I'll link back to that, basically discussing his idea that fructose drives oxidative stress and drives fat production, and that's why it's so harmful. And we'll talk maybe a little bit in relation to that, because it is directly related to this new premise, which is that it's not just the oxidative stress and de novo lipogenesis directly from fructose, but that fructose increases uric acid, and that causes oxidative stress and all sorts of damage. And another reason why I think it's pretty important that we discuss this is because these ideas, both Robert Lustig's and then Rick Johnson and David Perlmutter, there's of course kernels of truth in them, but the biggest issue that we have is that they're blaming fructose as the cause for all of these disease processes and everything, and the way that they are using certain mechanisms, more or less maybe out of context, you could say, we'll discuss that context, to support their view, really ends up being incredibly dangerous and harmful, because it directs people to think that fructose is the driver of all of these problems, as opposed to maybe being an innocent bystander, or even something that can help support our health if we do have these problems, as long as it's used in the right context. And so it's distracting from a lot of the underlying drivers of these disease processes that we discussed at length in our fatty liver disease series, in terms of endotoxin and polyunsaturated fats and on from there. So we'll be getting into that a little bit today. And in a moment here, I'll mention, I guess, kind of their main general arguments in terms of fructose and uric acid. But is there anything you want to add in first, Mike?
No, I just think that overall, if you start to look at fructose as the main driver of everything that's going on, you can get lost in seeing what the other possible candidates are or that are problematic. And when you actually start, again, parsing through the research and parsing through the arguments that they're making, you start looking at the particular nuances, you start to realize that the overall premise for which they're making their argument is, it's on shaky ground. And it's not to say that portions of what they have to say and the pathways aren't true. It's, again, as you mentioned, I think it's really important, the context with which these pathways become important. It's the same thing that we kind of talked about with Lustig. I mean, there's a bunch of different theories floating around for a bunch of different things, but this one I think is pretty prominent. And this one is a big, another big antithetical piece to a bioenergetic perspective. Kind of like the hormetic approach is the antithetical piece to the bioenergetic perspective. So definitely important to dispel a kind of half-truths or non-contextually based arguments.
Yeah, 100%. And so with that, I'll kind of just go over a summary of their main argument and then some of the nuances there, and then kind of give our main counter argument, and then we'll dig into all the individual points. But so their general argument is that fructose, when consumed in high quantities, is largely responsible for diseases, all sorts of chronic disease, insulin resistance, diabetes, metabolic syndrome, aging, obesity, everything that is degeneration. And the argument there is that when fructose is consumed in large amounts, it causes ATP depletion, causes low ATP, which then, when we'll go through the reactions and pathways, but then leads to uric acid production, which then causes oxidative stress. And that oxidative stress is the driver of all of these disease processes. And the kind of secondary part of this argument is that this is specifically a problem for us as humans, because we don't have the enzyme uricase, which allows us to metabolize uric acid. So because of this, we're supposedly very sensitive to fructose intake, causing these issues. And so as a result here, they end up recommending for a low fructose diet. They aren't fully anti-fruit. They say some fruit's okay. We'll talk about that. But they certainly are against fructose on its own and concentrated sources. And even considering other things that, there's other things that can increase uric acid that are high in purines, which ends up being any meat, but especially like organ meats and things. They do talk negatively about those as well, but we won't dig into that as much. It's just kind of adjacent to the fructose uric acid situation. But so that's kind of their general argument. And as I was saying at the end, there's this uricase piece, and that's basically there were certain genes that allow for most animals to break down uric acid, but certain animals, specifically apes, like there's a lineage of us and pretty much all the other, like they call them New World monkeys and apes, don't have this uricase enzyme. And they basically argue that this is something that allowed for us as apes to get fat when we had fructose, some amount of fat, in order to survive through famines and to survive through winters. And this is carried on. And now there's an evolutionary mismatch where we don't need to survive through famines and through winters anymore because of our modern world. And so now this mechanism that was helping us before is now working against us. And Rick Johnson's book title is just like a perfect, it encapsulates this idea exactly. And the title is Nature Wants Us to Be Fat. And I very much disagree with that statement to begin with, and we'll kind of talk through why. But it's very much built upon the same kind of neo-Darwinian evolutionary view that we discuss quite often, where whatever gets passed down is first the product of random mutation, and then is the product of allowing for survival in really harsh conditions. And that is, that's what's allowed for us to get to where we are. And it's all just random that we've become as complex and intelligent and whatnot as we are. It's just because we've been able to survive when other beings can't, as opposed to the more alternative view, the more even Darwinian or Lamarckian and on from their view, that basically discusses that improved functional capacity allows for things to get passed down, and there's a direction to those mutations and everything. And obviously that's beyond the scope of this conversation, but yeah, that's like a huge premise that we'll be digging into, is this idea that we just have this evolutionary mismatch, and that's why fructose is now bad for us when it wouldn't have been, and it isn't for other animals who have uricase.
Yes, original sin. Our human nature is leading us awry, and we have to go counter to our human nature and avoid all the sweet fructose laden foods, so we don't get diabetes and obesity and heart disease and gout, etc.
Mm-hmm. Yep. If we just give in to our natural way of being, we end up, fat and lazy and unhealthy. Of course, that's what we are as humans naturally.
Of course, exactly. Doesn't match any historical trends, but that's fine.
Right. Yeah, and interestingly as well, there's another piece that I've listened to some of these interviews with Rick Johnson and David Perlmutter. And Rick Johnson is even discussing how central ATP availability is, and talks about how the inhibition of mitochondrial respiration is what leads to, even in terms of fat gain and things, is that leads to hunger while also causing fat storage at the same time. But he just argues that fructose causes that. And it's pretty astounding that you can have that perspective and then still blame fructose. We talk all the time about the things that block the conversion from food to energy and cause it to then be rerouted and stored as fat. And those things that block energy production being the drivers of degeneration and the things that inhibit us from improving our health. And fructose certainly not being one of them, except for the extreme context that we'll get into. But so many other factors that actually do really directly and dramatically affect that process that supposedly are all secondary to the fructose that we're eating.
Yeah, I don't have too much more to add there. I think we should let's just jump in and start to talk about, what the main I guess the two arguments that you have laid out is, the first one is the fructose uric acid situation, right? So we'll go through all the specifics of that, the problems around it, etc. And then this evolutionary idea of humans, lack of uricase, increased uric acid, increased body fat, etc. So those are the two central arguments that we're going to parse through. And the first one we'll start with is the fructose uric acid connection.
And before we do, just real quick, just to kind of give our general counter argument, just so that people have an idea of where we're going. Basically, what we'll be describing is that fructose can increase uric acid and that uric acid can be a problem. But essentially, this is only going to happen if you're consuming fructose in very
Really
abnormal
large
ways,
quantity,
extremely large quantities, really high concentrations, like fructose only type beverages, which don't exist, or I mean, to my knowledge,
largely don't exist. Yeah.
Yeah. And not only that, but there also needs to be a dysfunctional system already in place. The body already has to be in a metabolically dysfunctional state. And the then next kind of conclusion there is that even in that context, fructose is not the driver of that dysfunctional state. So reducing fructose is never going to be the solution there. And that, of course, these sorts of massive, large quantities of fructose would never even be like reached, even if you were drinking like a decent amount of soda and things. But of course, also if you're making any effort to eat well and you're not having like multiple cans of soda per day, then it's especially irrelevant. Yeah, exactly. So that's kind of the premise that we'll be going to. And again, this is very, very similar, very parallel to Robert Lustig's argument, where he lays out all these pathways of what can happen in basically the worst scenario of this already really dysfunctional system. You add in all these super high concentrations of fructose, and it increases de novo lipogenesis, drives oxidative stress, and they do the same thing with the uric acid pathways. And yes, it's true that those pathways exist, and fructose can drive them, and it's true that they are relatively harmful in terms of they exist in a dysfunctional state, but that again, they don't happen when our bodies are working properly, when we have a solid metabolism, or at least don't have an extremely deranged metabolism. And then also, this deranged dysfunctional metabolism isn't caused by fructose. And so those are kind of the points that we'll be discussing.
Yep. And basically, when you actually go through the research and instead of looking at the interpretation, you get a pretty vastly different picture, even with the Robert Lustig piece of like fructose goes to the liver and then you have de novo lipogenesis and fat production. And you wind up looking through the studies and like, yes, less than 1% of fructose goes to de novo lipogenesis. And then the vast majority goes to glycogen, glucose, lactate, and energy production. And so we're going to break down those nuances directly here. And specifically, we can talk about Lustig a little bit because the argument can come into play to some extent, but the main focus is around the uric acid situation.
Yeah, definitely. And there's so many other factors that are involved here too, right? Like you mentioned the pathways for fructose, and there's many other confounding variables. We talked about endotoxin and polyunsaturated fats and iron and things like that are all massively confounding variables, not to mention the way the research is performed, that it's often done on rodents, and the problems with directly correlating that to what would happen in humans. Again, the way the fructose is given. So we discussed all of that before. And again, as you're saying, it's very parallel and to what we'll be describing today. And again, it's like the way that they're presenting it is as if that is the only way that things happen. And it's a nice story, but it's just not it's not the full picture.
It's a hypothesis at best, especially with the connection to the evolutionary piece.
It's just a part of the bigger picture. I mean, there's truth there. Like, sure, we can say hypothesis, but it's like that pathway exists. Fructose can go down that pathway, and we'll discuss that. But there's massive pieces of context that are missing that make this inapplicable to humans in our regular lives.
Regular setting, yeah.
All right. So as you mentioned, we'll first be discussing the fructose to uric acid situation, and we'll kind of go through these pathways and then also the physiology of when this is happening and why it's happening and why it's not particularly relevant to us consuming fructose in normal ways. All right. So the first piece here in that fructose to uric acid pathway process is that, and the first part of the argument requires that fructose depletes ATP. And we'll show on the diagram why this is important in a second. But there is this argument that fructose is going to deplete ATP in the liver compared to another carbohydrate like glucose. And that's because there's a lack of regulation at certain steps in what's called fructolysis. It's kind of the parallel to glycolysis. And that lack of regulation supposedly is going to leave this process unchecked. And so you're going to get a lot of ATP depletion, which I'll show in a second. And that's going to then lead to the uric acid production. So that's kind of the first piece here that we'll dig into. I'm going to share a diagram showing that pathway. So you can see here on the right that this is fructose coming in, and this right side of the pathway here is the fructolysis, basically. On the left side here is the glycolysis. So you come here, and the glycolysis continues all the way down to here until you get pyruvate to acetyl-CoA into the Krebs cycle and on. And fructose, basically, there's a couple of steps, and then it enters into glycolysis. And so the main argument that's being made is that this first step here by fructokinase requires ATP to be converted to ADP. And the argument is that there's no regulation that's going to go on here. And so when you get a lot of fructose, they just say when you get fructose, it's going to cause this massive depletion in ATP because of this first step. And the regulation of glycolysis happens a little differently. So with glycolysis, this part on the left, there's certain features of metabolism that when things are slowed down, it slows down certain aspects of glycolysis. The first of those is phosphofructokinase right here. And so this gets inhibited by citrate when there's a buildup of citrate due to impaired respiration or slowed respiration. And then there's also some inhibition up here from the glucose entering the cell through the GLUT2 receptors, which along with like that GLUT2 receptor involves glucokinase. So because there's limitation here and limitation here, the argument is that if you got the equivalent amount of glucose, then you wouldn't get a huge ATP depletion like you would with fructose, because this step is not going to happen. It's going to be stopped up. And we'll talk about how relevant that is, but it's important to note, again, the context here. And so when there is not a situation where respiration is inhibited, we shouldn't have to worry much about that step, because what happens is after that first step from fructose to fructose 1-phosphate, it then continues on and ends up into the, there's these couple of different pathways here to end up into glycolysis as glyceraldehyde 3-phosphate. And then it's going to continue down. And throughout glycolysis, you're then going to produce ATP at two different steps. So you've got the phosphoglycerokinase and then also pyruvate kinase. And both of those are going to lead to two ATPs being produced. So if there's not an inhibition of respiration going on when you have fructose entering in this case, the liver, then what's going to happen is you're going to deplete a tiny bit of ATP, just like you would with glucose, but then it's going to continue down this pathway, and you're going to end up with a net of 2 ATP by the time you've gotten to pyruvate. And then once pyruvate continues on through the Krebs cycle and then to the electron transport chain, you're going to end up with way more ATP. You're looking at around 36 ATP in total or so. And so the main point here, and I'll let you speak in a second, Mike, but basically is that you're not going to have major ATP depletion unless there's already a problem going on where you have inhibited respiration, or that respiration is going too slow to make up for or to take up or to deal with the amount of fructose coming in. So we have these two situations, one which is insane amounts of fructose will cause like a clog here where you're just depleting that ATP right away and you just don't have enough time to get farther down and produce more. Or you have the situation where mitochondrial respiration is inhibited. You end up with a low NAD to NADH ratio. So you have inhibition over here in glycolysis. You have inhibition at pyruvate dehydrogenase. You end up with the buildup of citrate, which I don't think is shown on here, but that buildup of citrate will then inhibit phosphofructokinase. So when that happens, then yes, you'll end up with a lot of the fructose getting stuck in these steps here, and you might end up with depletion of ATP. But again, that's only going to happen when respiration is inhibited or you have huge bolus amounts of fructose.
Yeah. So essentially, basically what you're saying is that glucose and fructose, as far as energy production goes in the glycolytic process, have the same net ATP production regardless of whether it's fructose or glucose. The only difference I guess a key point of the argument, the only difference is that there's a lack of regulation at fructose kinase like there is at glucose kinase and phosphofructose kinase 1 with fructose versus glucose. So in the situation where the system is backlogged down by after glycolysis, so around the Krebs cycle, with it build up a citrate, etc. If this stuff in the back here is all backlogged, then glucose will not be able to enter the cell and be able to oxidize through or move through glycolysis to move into the Krebs cycle, whereas fructose should be able to do so. And in doing so, because it requires ATP in these initial steps, it can deplete ATP in the cell. And this first step is irreversible. So essentially, you'll start building up this fructose 1-phosphate and depleting ATP, and then that is like the first key point of the entire argument. And as you're pointing out here, is requires a context. So the context requires that cell respiration is essentially backlogged to some extent,
Mhm.
or you have a massive dose of fructose all at once. So
Mhm.
essentially, you need to have altered metabolism to begin with, or you need to have a massive doses of fructose in order to push this process to occur, particularly in humans.
Mhm.
So the other thing to keep in mind, and I guess we'll get into this a little bit later, but a key point is in as far as the backlog and metabolism, well, in those situations, the fructose isn't necessarily the direct problem. The direct
Right.
problem is the backlog. So the idea would be to address the backlog. Now, not having large boluses of fructose in those situations may be helpful, of course. But in the other situation with the large boluses of fructose, there's multiple problems involved besides just the idea that too much fructose at once is going to deplete ATP. The first piece is that in humans, there's a limited absorption of large boluses of fructose. So in those situations, if you don't have glucose present, and a lot of the studies look at the effects of large boluses of fructose without glucose. So if you don't have that glucose present, you won't absorb that fructose, and then you can actually see an increase in endotoxin production inside the intestine and subsequently portal circulation. So you get endotoxemia. So you get an influx of endotoxin. So what is great at stopping up metabolism in the liver? Endotoxin. So that is a big confounding factor to this overall picture. And then the second point is that in order to get specifically around the fructose, in order to get large boluses of fructose in nature, unless you're pounding agave syrup, you would have to, or just like slamming ridiculous amounts of apple juice, you would have to eat large amounts of glucose concurrently. So if you wanted, in a lot of the studies, they'll do like a 75-gram bolus. And we're going to get into this, but you have to do a
Mhm.
75-gram bolus of fructose. In those situations, you would have to be taking in 150 grams of carbs in one sitting usually, and because most fructose is accompanied by glucose. So you have so in both situations, you either have some type of metabolic perturbation in the system that is leading to this backlog all the way back through glycolysis, and we've covered this before. What that process actually looks like. We talked about in hormesis. We talked about in the fatty liver series. But then on top of that, you also have a situation where if it's just the large boluses of fructose coming in, number one, in most natural settings, it doesn't usually occur to have that type of situation. And then number two, if it does occur, there is also a confounding situation of endotoxemia. So it makes it difficult to parse out some of those effects, especially with the known effects of endotoxemia on liver respiratory metabolism. So
Mhm.
there's a lot more to the picture overall, and even if the argument sounds simple to start.
Absolutely. And those are all great points, all major factors to consider in terms of the argument. There's a couple others as well. So the first, or not the first, but another thing I would mention is that this isn't the equivalent of like depleted ATP that we're talking, like the fructose coming in, even in a high concentration, is not the same as what we're normally talking about when we're talking about low ATP being a driver of various issues or low energy production or inhibited energy production. There's nothing actually being inhibited here by the fructose using that ATP and converting it to ADP. This is instead just a transient, short term depletion of ATP that, as we talked about in the long term, and not even that long, we're just talking like relatively speaking, is then going to be continually oxidized all the way, assuming respiration is working properly. And then you'll end up with extra ATP. So this is, again, very much short term. And it's just a kind of like a physiological side effect of, again, something that, as you're saying, is not really anything we would experience in a normal context due to the nature of not having fructose alone when we're having any carbohydrate source, even if it's table sugar, that's half fructose and half glucose in a molecule called sucrose. And so you're getting the glucose there, as you said, to help with the absorption and prevent endotoxin absorption and or production and fructose malabsorption and everything.
And you also have glucose moving through glycolysis as well. So you also have
To keep
another
things moving. Yeah.
exactly. So you have two different substrate moving in that picture, which also
Mhm.
can alter what's going on with fructose.
Right. Which is, a point as well that if the liver is stuck oxidizing fat, then that is something that would also inhibit glycolysis. And, we've talked about that in the fatty liver series as well. So, so those are all like important factors to consider. And there's considerable research, as we were kind of alluding to, with what's required in order to get this ATP depletion being kind of absurd. And so we'll go through some of those studies in a moment. But the other piece of it as well is that outside of those contexts, it's hard to even create a situation where fructose is depleting ATP, and normally it's doing the opposite, and it's extremely protective. So I'm going to share a quote here in a second, showing that this is what happens in the context of hypoxia-induced liver injury, hepatocyte injury. So again, this is showing that even in a compromised state, fructose is generally going to be protective and prevent ATP depletion and support the NAD to NADH ratio and everything. So this is a study titled Modulating Hypoxia-Induced Hepatocyte Injury by Affecting Intracellular Redox State. And they state that hypoxia-induced hepatocyte injury results not only from ATP depletion, but also from reductive stress and oxygen activation. Glycolytic nutrients, fructose, dihydroxyacetone, or glyceraldehyde, prevented cytotoxicity, restored the NADH to NAD ratio, and prevented complete ATP depletion. So again, showing that fructose prevented the toxicity, the cytotoxicity, the cellular death and damage in this state, restored the NAD to NADH ratio, and prevented ATP depletion. The next part here is talking about alcohol or ethanol. And it's funny because alcohol and fructose are always compared as being very parallel, very much the same. Something that Robert Lustig did, and it's something, again, that's done by Rick Johnson and David Perlmutter. But it tends not to be the same. It tends to have opposite effects. And so they state here that ethanol, which further increased the cellular NADH to NAD ratio increased by hypoxia, also markedly increased toxicity. And then they state, furthermore, increasing the cellular NADH to NAD ratio markedly increased the intracellular release of iron. And we'll talk a little bit about iron later on. It's not a major player here, but something we talked about in the fatty liver series, and something that's always relevant when we're looking at an energy depleting situation and inhibited energy production situation. Then they finish off here and they state that hypoxia-induced hepatocyte injury was also prevented by oxypurinol, a xanthine oxidase inhibitor. And the reason why I was including that is because again, kind of this thesis that fructose increases uric acid is then dependent on allopurinol or oxypurinol, things that inhibit xanthine oxidase, which we'll get to. Those have to have opposing effects to fructose, because if fructose is the thing that's increasing the production of uric acid and causing all this damage, then it should be having the opposite effect of a xanthine oxidase inhibitor. And that's something that's pointed to by Rick Johnson, for example. But here you're seeing that both the fructose and the oxypurinol protected the hepatocytes in this scenario. So I don't know if there's anything you want to add in here, Mike.
The interesting thing that came out of this study was also that what was really important in protecting the cells was actually avoiding reductive stress. So avoiding that buildup of NADH to NAD, which is actually, I know there's a recent podcast where there's some question about that. It's like a round table deal, but
yeah, apparently reductive stress doesn't exist, Mike.
Yes, there's no such thing as reductive stress. But they what they talk about is that in this hypoxic situation, the ability of fructose to actually enter into the glycolytic situation and basically help to recycle some of the NAD and NADH by oxidizing the NADH and moving through through glycolysis was actually rescuing the cells in this situation. And they adjusting the NADH to NAD ratio was helpful overall, even if ATP, I think they compared other situations where they were looking at if it actually restored ATP. So fructose did restore some of ATP in this situation. And they actually have a graph pulled up, and I won't pull it up because it's kind of confusing to look at. But there's a graph here where it did restore some of, I think it was like at 90% ATP at an hour, and then 40% at 2 hours. And then also it increased lactate and pyruvate because it went through, the cells eventually went through lactic acid fermentation to produce their energy. But that recycling of the ratio is extremely important. And then also maintaining ATP as well. So reductive stress being a huge picture here and extremely important to the situation. And this is also extremely important to consider overall, because when we're talking about having a backlog in the system, that backlog in the system often results in a reductive stress type of situation. And so they also looked at beta hydroxybutyrate in this situation, which is keto acid, and it's involved in fatty acid metabolism. And basically, they're saying is it reduced mitochondrial NAD, increased lactate and pyruvate ratio, and also increased hypoxic cellular and cell injury, but did not prevent ATP depletion. So the reductive stress being like a central point here in this overall piece, and is also this is very specifically important. So you're looking at hepatocytes, but when we're talking about the backlog, that being an element of this backlog in the cells for their energy production.
Yeah. Yeah, 100%. And again, just to highlight here, we're talking about one of those situations that we were saying, an already dysfunctional system, and adding just fructose, and it was still able to not only restore the NAD to NADH ratio, but also prevent ATP depletion and increase ATP. So a pretty dramatic thing to see when, again, there's arguments of fructose doing the exact opposite in an already healthy person, let alone in a dysfunctional state.
Yeah, and so the other thing too is they added dihydroxyacetone and glyceraldehyde, which are metabolites as well, and they also rescued the cells. So both fructose and then these other glycolytic metabolites from the metabolism, I think, is of fructose through that pathway, was able to rescue the cells from the reductive stress that eventually led to a whole host of like ROS and then iron and xanthine oxidase, et cetera.
Yeah. So the next piece here in the next part of their argument is that the ATP depletion that is supposedly happening in whatever context from fructose is then going to increase the production of uric acid. That's going to cause all sorts of issues. So we're just going to pull up the pathway showing how fructose can end up producing uric acid.
So essentially what we just described in the previous post or the previous graph that we pulled up was that first step in glycolysis or fructolysis specifically causes an irreversible utilization of ATP. Exactly. There you go. And then you get this ADP that's left over. If that happens rapidly or the system's backed up, then the ADP essentially gets converted into AMP. So just as a quick briefer, so ATP is adenosine triphosphate, ADP is adenosine diphosphate, and an AMP is adenosine monophosphate. So what essentially happens is when you have this ADP, it gets converted into adenosine monophosphate, and then adenosine monophosphate deaminase gets converted into inosine monophosphate, and then you have the 5 nucleotidases that convert inosine monophosphate to inosine. The adenosine monophosphate can also be converted. You also get the adenosine, and then the adenosine gets converted into inosine. So inosine, now we're in this purine pathway, and the inosine gets converted to hypoxanthine by purine nucleosidase phosphorylase, and then eventually you get hypoxanthine. And then you have, now this is kind of where you get to a sticky situation that we're going to address directly, but you have this enzyme xanthine oxidase. Now there's two forms of this enzyme. It can either be xanthine oxidase or xanthine dehydrogenase, and the enzyme is dependent upon the cellular context, how it functions, and what type of xanthine oxidase enzyme, or I think it's what do they call it? Xanthine oxidase reductase?
Oxidoreductase.
Oxidoreductase, depending upon what the state of the cell is. It can be either dehydrogenase or oxidase. And essentially, this enzyme catalyzes two steps in this uric acid production pathway where hypoxanthine is converted to xanthine and then converted to uric acid.
So the big picture here is that fructose can get converted to uric acid through this pathway. If there's excessive amounts of ATP depletion, you've got excessive amounts of movement through the step, you're not properly repleting, converting that ADP back to ATP, whether it's here or through the other steps of glycolysis. So in that situation, you get fructose being converted all the way down these pathways through to uric acid. And this is the focus generally from David Perlmutter and Rick Johnson. And so what we'll talk about next is the situations where this happens. And as we said, they tend not to be particularly relevant to how you might eat.
Yeah.
How us as humans typically eat. So there was a meta-analysis done to consider all the studies looking at fructose and when it does and doesn't increase uric acid. And so I'm going to share some quotes here that describe a lot of what we've been discussing. So the title of the study is "The Effects of Fructose Intake on Serum Uric Acid Vary Among Controlled Dietary Trials." And so they state that there's concern that dietary fructose may increase uric acid concentrations. To assess the effects of fructose on serum uric acid concentrations in people with and without diabetes, we conducted a systematic review and meta-analysis of controlled feeding trials. So here's what they found. They state that isocaloric exchange of fructose for other carbohydrate did not affect serum uric acid in diabetic and non-diabetic participants, with no evidence of interstudy heterogeneity, meaning that it was homogeneous. So everybody had basically the same response here. There's not a question of maybe individuality between the studies. And they then state that hypercaloric supplementation of controlled diets with fructose at 35% excess energy at extreme doses of 213 to 219 grams per day significantly increased serum uric acid compared with the controlled diets alone in non-diabetic participants, with no evidence of heterogeneity. Confounding from excess energy cannot be ruled out in the hypercaloric trials. These analyses do not support a uric acid increasing effect of isocaloric fructose intake in non-diabetic and diabetic participants. Hypercaloric fructose intake may, however, increase uric acid concentrations. So in a second, I'll be digging into those studies in a little bit more detail, the ones that included the excessive amounts of fructose. But again, just to highlight, so what they said was that in both diabetic and non-diabetic participants, replacing fructose for other carbohydrates had no effect on serum uric acid in all of the studies that they looked at. The only situation where fructose was increasing uric acid was in hypercaloric supplementation of controlled diets. So someone's already eating a regular diet, and I'll get to that in a second, and then adding 35% of their calories that they were already eating, so a total of 135% of what they would have eaten on their controlled diet from pure fructose, from fructose sweetened beverages. And in that case, which was an extra 213 to 219 grams of pure fructose, that increased serum uric acid. And this was in non-diabetic participants. And so they state this in a little more detail, where they say that the 3 hypercaloric trials in this meta-analysis fed fructose at 35% excess energy, which was 850 to 870 calories, or 213 to 219 grams, in fluid form in non-diabetic males for 1 week, a level of exposure that is more than double the 95th percentile of fructose intake in the United States. And then I looked at those studies that included the hypercaloric fructose feeding studies, and found a couple other details. And that's basically looking at what the diet was. And so that 35% calories of fructose was a 20% fructose sweetened solution. So they're just drinking very, very concentrated solution of fructose. And again, this is 35% more than they would normally be eating, which is a huge amount. And that was on top of a controlled diet that already had 55% of its calories from carbohydrates and contained 11% of those carbohydrates as sugar. Another interesting piece is that in this study, they limited leisurely sports activity to less than 1 hour per week. So basically, they weren't allowed to be active during this time, because that would confound the studies. So they're eating an already high carb diet with some amount of sugar, and then adding it's a huge fructose overfeeding study with solely fructose. And that is the only context looking at, this was a meta-analysis of all the studies looking at fructose in place of other carbohydrates. And this was the only situation where they actually found it to increase uric acid levels.
Yeah. I mean, I have a couple studies here that look at similar situations. So, and this is characteristic of most of the research in humans around fructose. So, I have another study here, essentially looking at the effects of with ATP homeostasis inside diabetics. So essentially, what I wanted to point out here is we're looking at what types of people that they're looking at. So the people who are eligible were between the ages of 45 and 76 years old, had type 2 diabetes, had a body mass index greater than 25, and were able to complete a maximal exercise test. So they were, first of all, we have people who are overweight. And so this is kind of their breakdown overall. Their normal dietary fructose intake. So these are the people who completed here, was about 17 grams per day. They usually ate 1,500 calories per day. And then here's we have their serum uric acid, and they were clearly overweight. And most of them were on drugs for diabetes. So
and Mike, this was an individual study, or this was a review?
This is an individual study.
Okay.
So
and so
go ahead.
Well, I was just going to say, so what you're describing right now is just a study where they were looking at fructose's impact on uric acid, and you're just saying that they were doing it in largely diabetic overweight
Exactly.
participants.
But furthermore, besides doing it, so I'm pulling out the studies that even in the meta-analysis, they reference some of these studies. So there's quite a few of these. And what they talk about here is that um, after an overnight fast, they infused, 250 milligrams per kilogram of body weight fructose. They infused it over 30 to 60 seconds. So at my current body weight at 200 pounds, 250 milligrams per kilogram would give me about a 23-gram bolus of intravenous fructose in a minute. So, and then what they basically saw from this study is that they depleted hepatic ATP content. And so my point in sharing this is that in a lot of these studies, another study they looked at a 75-gram bolus fructose like oral drink in 5 minutes. So what happens in a lot of these studies is, particularly for an intravenous study, you never will see that level of fructose in the bloodstream ever.
Yeah,
It's the liver takes all of the fructose that you get from gut absorption, and the other thing is your gut will parse or slowly drip the amount of carbohydrate that you'll be absorbing from your diet over time. So it'll adjust its influx. So an intravenous dose or things like that, yes, you see ATP depletion. Of course you will, because you have a massive bolus of fructose intravenously. And then in the oral dosing studies, again, like I discussed previously, in order to get 75 grams of fructose in an oral bolus in normal consumption patterns, you'd have to have at least or around 150 grams of carbohydrate. So what you're essentially saying here is, I'm going to slam 150 grams of carbohydrate at one time, or in this case, 75 grams of fructose. That doesn't count for any type of malabsorption or intolerance, etc. And yes, you're going to see metabolic perturbation. So in these circumstances, you will see ATP depletion in the liver, no problem. There's no question about that. There's no argument about that in any place. But the question is, do any of these situations mirror real life? And the answer is no. So what you wind up seeing is, there's a couple other studies that they talk about.
Real quick, Mike, just because you were talking about the injection ones. So just for reference, in terms of glucose, which you always have glucose in the blood, you don't normally have very much fructose. In terms of glucose, if you have a low blood sugar of, let's say, 80 milligrams per deciliter, then you're normally having about 4 grams of glucose in your blood at that time. If you eat a super huge, like very carbohydrate rich, easily digested meal and doubled that to a blood sugar of 160 milligrams per deciliter, which is high after a meal, depending on what it was, but talking a big, very carbohydrate dense meal, then you would have 8 grams of sugar in your blood. And the study you're talking about, as you said, would be injecting as much as 20 grams of fructose. Yeah, 23 for someone who's 200 pounds, grams of fructose into the blood directly, which is incredibly high. I mean, we normally have very, very little fructose. Like, we have way more glucose than fructose in the blood. And even if you were adding that much glucose, I mean, that would be the equivalent of, oh man, what would it be? So 20 grams would be like 400 milligrams per deciliter. Is that right?
So if you're at 80, so you want to get to 20, you have to be by 5. So yeah, 400.
Yeah. So adding, the equivalent amount of glucose would be putting your blood sugar at a level of 400 milligrams per deciliter, which even, like, you have to be very, very extremely diabetic to hit anything near that. So yeah, this is not at all related to like a physiologic.
Not to mention that the population that they tested this in was diabetic, and they were using metformin. Almost 50% of them were using metformin, and 50% of them were using, I can't even pronounce the name of the drug, thiazolidinediones. So they were using other diabetic drugs. Mm-hmm. So you already have it. You're taking an impaired population and injecting them with a ridiculous amount of fructose, and then wondering why they had, or basically saying, look, here we have hepatic ATP depletion. It's like, yes, you're going to have hepatic ATP depletion, especially in diabetics. It's like, that's not even a question. So, there's a couple other studies that I went through specifically, and that the review talks about, because I wanted to see, like, what are we looking at in this research in humans for fructose and ATP depletion. And again, there's different situations. So you have a situation where you have ATP depletion, which is where the fructose is rapidly entering the liver. It's undergoing fructolysis, and then you're using up that ATP really fast because you have such a massive dose. So like the 23 grams IV. Other situations like a 75-gram bolus, and then The other thing after that is if you have ATP depletion, then the next studies are you looking at uric, like what happens with uric acid? So as far as the and the uric acid piece comes in through that step that we talked about, where you start moving the ADP to AMP to inosine and adenosine, and then those get converted to uric acid through some of the nucleosidase enzymes, and then xanthine oxidase or xanthine dehydrogenase. So the first problem is you have these massive boluses with all of those situations. The next problem is, or the next thing that they say is in this review, they say, however, it was recently reported that ingestion of larger amounts of fructose failed to acutely increase uric acid concentration when ingested in split doses throughout several days, suggesting that liver ATP depletion is unlikely to occur with usual patterns of sugar consumption. So we have research looking at, okay, what if we split these doses up over time? And we see, okay, well, that's not really a problem. The other thing that we talk about is if you have like a metabolic syndrome, does that increase your probability of having this uric acid problem? And again, that goes back to having this backup of energy metabolism, right? So you have your glycolysis already backed up. So the way they look at this is they can look at if in type 2 diabetics or people who are overweight. And what they then turn around and say in the research is Lin et al. Observed that fructose consumption resulted in higher serum uric acid in individuals with a BMI greater than 30 kilograms per meter squared. Interestingly, their studies show that there was no effect of fructose intake in subjects with a BMI between 25 and 29 kilograms per meter squared, although serum uric acid showed a trend to be elevated depending on body weight status. Moreover, the blood samples were drawn after an overnight fast in the morning, ruling out any postprandial effects of fructose ingestion. Additionally, the effect on serum uric acid was more likely to be secondary to obesity or metabolic syndrome than fructose consumption per se. So now what we're seeing is that being in metabolic syndrome and then throwing in large boluses of fructose is likely to increase uric acid, most likely because the context of that backed up metabolism, and less so because there's like fructose is inherently a problem. You already have a metabolic problem, and then you're throwing fructose into the system, and it may exacerbate issues, especially in larger boluses. And again, I want to preface again the context here. In all of these studies, we're talking about free fructose. We're not talking about they're giving people orange juice, which is a very different scenario overall.
Right. Yeah. 100%. And again, the difference you're alluding to there is that orange juice would have equal amounts of fructose to glucose, more or less. There's also other factors like the polyphenols and vitamin C in there that help to deal with uric acid, but we'll get there later. But yeah, very different. Even fruit juice, which according to people like Perlmutter and Rick Johnson, I've heard them say that, you might as well just be like drinking straight fructose. It's the same thing, it's the same as drinking soda. Like avoid fruit juice for sure is their recommendation. And of course, Robert Lustig as well.
Well, and there's also a study here looking at what happens if it's fructose and glucose compared to just fructose. And what they wind up saying here is, I'll just read it here. So Akhavan and Anderson tested solutions containing different ratios of glucose and fructose. And their study, overnight fasted men receive a standardized breakfast in the morning. At 4 hours later, a 300 kilocalorie drink was ingested within 3 minutes. The solutions were sweetened with either high fructose corn syrup containing 55% of fructose, sucrose, or the monosaccharide forms of glucose and fructose in specific ratios. So there was an 80% glucose, 20% fructose. There was a 50-50, which was sucrose. There was a 35% glucose, 65% fructose. And then there was a 20% glucose, 80% fructose. At 75 minutes, uric acid concentrations were highest after the 20% glucose and 80% fructose drink. The sucrose and the 50% fructose and 50% glucose solutions each resulted in significantly lower uric acid concentrations than did the 20% glucose, 80% fructose solutions, but they did not differ significantly from any of the other solutions. The uric acid area under the curve did not differ significantly after the glucose 35 and glucose 35, fructose 65, glucose 50, fructose 50, and sucrose solutions. In other research, only a weak response of serum uric acid to fructose was found. So in layman's terms, or in, I guess, more simple terms, because it could have been a little confusing there, but essentially only in the solution that was 20% glucose, 80% fructose, did you see a higher serum uric acid concentration, or that was the highest. But when you add 50% fructose and 50% glucose solution, there was significantly lower uric acid concentration overall, and it did not differ significantly from other solutions. And then the uric acid area under the curve did not differ significantly. So essentially what you're seeing is that if you have glucose present with fructose, which is, again, this is the normal consumption pattern. You don't get people having 100 grams of fructose in a bolus in a drink and taking it in 30 seconds or 2 minutes. That's not what happens for most people. And even if you're having high fructose corn syrup, which is only 55% fructose, you still, again, that's very close to the 50-50. We're not seeing this massive difference. So it's hard to even pin it on high fructose corn syrup. It's more of a question of, in these studies, like where you're not getting this straight bolus of fructose. And if you put glucose with it, you get an entirely different result. If you space out consumption, you get an entirely different result. And you wouldn't be able to hit these dosages of fructose in the studies anyway. So it's like the other thing is you're not injecting fructose in your veins either. So in all of these situations, it's like, let's test this extreme context. And then we're going to make these extensions about how terrible fructose is. And then look at some types of epidemiologic research and see people who have soft drinks have X outcome. And it's probably because of the fructose, because of these extreme studies. It's a very, that doesn't take the context into focus at all. And there's some historical stuff that we can talk about as well. But go ahead, Jay.
Yeah. There's a lot more to dig into. It's like, if that's the line, if that's the threshold we're using to define something as a poison, like it's meaningless, right? I mean, at that point, water, if you drink all of the day's worth of water in like 2 minutes, depending if you're drinking, an ounce per pound or more, whatever, you can drown. And so water is obviously a poison as well. And I mean, it's just absurd to pull out of these contexts and then make a claim that fructose itself on its own that is the problem. Let alone, and it is the driver as well, let alone just something that's added to a poor context in ridiculous amounts.
The other piece I was just going to touch on from this was they talked about like a contextual examination of sucrose consumption over time. And essentially what they were showing in some of this research is that, so the specific quote here, they say, in this respect, a recent New York Times article by Strom pointed out that due to incorrect methodology, as discussed by Muth, so it's a researcher, U.S. sugar consumption in recent years has been overestimated by 20%. Interestingly, the author implied that sugar consumption has not risen since the 1980s. This makes many assumptions based on higher production or per capita consumption data unsubstantiated. In addition, data obtained from the U.S. National Health and Nutrition Examination Surveys 2005 to 2010 concluded that total energy from added sugar remained rather constant, or even declined in some segments of the population in recent years. Moreover, the consumption of added sugar through beverages contribute to only 1/3 of total added sugar intake, indicating that energy from added sugars mostly came from foods rather than beverages. So that's another extremely important piece that I want to point out here is where are these added sugars coming from? If you're coming from like a packaged food, I would say the most likely place, at least considering the United States, the U.S. lifestyle, would probably be some type of baked good, some type of cookie, bread, something along those lines that contained other ingredients that may be problematic. But overall, what we're seeing here is that the trend for consumption of these beverages is not increasing. And they're saying since the 1980s, which doesn't track the idea of the increasing obesity, heart disease, et cetera, trends. So it makes it like even the epidemiologic data is questionable as far as is sugar tracking with the trends of these diseases. So that's another piece to put into consideration.
Yeah, and there's that graph put together by maybe Stephen Guigné with showing that sugar consumption has actually decreased.
Yeah.
In the last 10, 15 years. But again, this is talking, I'll see if I can pull it up, but again, this is talking about the the average public, the average population, not people who are trying to be healthy, not people who are actually going out of their way to avoid, soda, for example.
Yeah. So we have context for humans where when they find the ATP depletion or the increased uric acid, the dosing, the method of dosing is just not realistic. And then furthermore, we have situations where the epidemiologic data is also may not necessarily be realistic or congruent with the trend of these disease processes. So we have a mechanism. We know that depletion of ATP through excess fructose consumption in like through injection of the vein or in large boluses can lead to these increases in uric acid. So that's established, and there's no argument against that. But what our overall argument is going to be from here is that normal consumption of fructose in the way that even normal US adults are consuming the fructose is not necessarily the cause of the elevated uric acid or the obesity and diabetes pandemic or endemics or whatever they are, etc. And that what's more likely, well, we're not going to offer another cause for there, but it's just that the fructose is unlikely to be the issue here overall. And we're also, I guess we'll have to dig into uric acid a little bit. I don't know what direction you wanted to take it next.
Yep. That's the direction.
Yeah.
So I found that graph real quick. I'll pull it up from Stephen Guigné. And he has one looking at carbohydrate intake and sugar intake, but it's just showing that basically from 2000, maybe it's right before 2000 on, not only has now it is the same as it was in 1980 because it came up and then went back down. But yeah, not only is it plateaued or anything, it's going down considerably. And maybe that's because, people are trying to be healthy or whatever the reason is. But yeah, it's going down as obesity is still steadily climbing. And then if you look at graphs looking at, for example, like vegetable oil intake, which, tracks very closely, very nicely with obesity.
Yeah. I mean, I have a table here too, looking at US average consumption liters per person of bottled water, cola carbonates, non-cola carbonates, sports drinks, and 100% juice. And basically what you see in this table is that, the cola carbonates in 2007, were at 71 liters per person. And in 2012, they're at 56. Non-cola carbonates were at 56 in 2007, and in 2012 were 55.9. So kind of consistent. Sports drinks were at 16.3 and in 2007. Now in 2012 were 17.3, and fruit juice consumption has actually decreased. So from 16.5 in 2007 to 14.3 in 2012. So just in this 5-year period, you're seeing decreases in the consumption of these foods overall, or of these drinks. And again, I mean, it's the sugar consumption isn't only going to come from the drinks. As they talked about, I think only 30% of the added sugars came from drinks. But those are usually what's discussed as being the problematic, or often the cliche problematic sources of fructose. And you're actually seeing decreased consumption of those. But we're not seeing decreased rates of these diseases or incidence and prevalence of these diseases. Some of them we're seeing decreased mortality from some of the diseases, like some of the heart disease, but the like incidence and prevalence isn't necessarily decreasing overall.
Yeah, those sugar taxes, the soda taxes must be working.
Yeah. Well, they actually talked about that in the article, and they found that the soda taxes increased the consumption of beer in the households that drank beer. So they stopped drinking soda and then they started drinking beer.
Oh man. Yeah, I've got another study kind of going back to what we were discussing before, just looking at the situation where fructose will increase uric acid, again, pointing to a lot of the things you mentioned where, people who are, this was 40 to 72 years old, high BMI, they're eating ad libitum diets and then adding just fructose sweetened beverages alone. And I'll add that study to the show notes along with all the others. But another thing that I just wanted to mention here is that in that study, they talked about how it also increased hepatic de novo lipogenesis. And again, these, as we kind of alluded to, those processes tend to go hand in hand, because when you're not able to fully metabolize fructose due to inhibited respiration for various reasons, nutrient deficiencies, PUFA, endotoxin, and on from there, you're going to get that excess ATP depletion that's not being repleted, leading to uric acid. You're also going to get de novo lipogenesis. So again, in that fatty liver series, we discussed this, and we discussed how you cannot, like, the situations where you have elevated levels of DNL are not relevant to us as eating it doesn't mean that we shouldn't eat carbohydrates or fructose for all the same reasons that we're describing with uric acid. So I just wanted to draw that parallel. But again, yeah, kind of, I think we've gotten this point across that essentially the context in which fructose is creating ATP depletion and then increasing uric acid is not relevant to us. It's not relevant to what we should be doing to be healthy. It's largely irrelevant. Now, the next piece here is the uric acid itself, and the question of whether the uric acid is this major culprit that it's made out to be, where it drives metabolic syndrome and it causes, insulin resistance and diabetes. And Rick Johnson and David Perlmutter, who are arguing for this, are saying that basically the reason why uric acid does these things and drives hypertension, increases triglycerides, all of that, is because it increases intracellular oxidative stress by stimulating an enzyme called aldose reductase, which then stimulates NADPH oxidase, which drives oxidation or oxidative stress. And then the other piece is that this will decrease AMP kinase and increase AMP deaminase. And then the last piece here, which is their kind of major evidence for this, is that when you block xanthine oxidase, which we'll get there in a second, but that's the enzyme that produces uric acid through that whole pathway, like at the end there, those last two steps, when you block that using allopurinol or a different purinol, it reverses all these symptoms of metabolic syndrome. And of course, they also point to the association, the correlation between metabolic syndrome, degenerative diseases, all of that, and serum uric acid levels. Of course, that's a situation where correlation certainly does not does not mean causation. But again, then they point to that if you block the production of uric acid, that does lead to benefits. So that does imply causation. So we'll kind of talk through a handful of reasons why these things are not the case. Uric acid is not just this,
toxic compound.
Yeah, it's not toxic. It's not a poison. It's not driving this metabolic syndrome, even if there are negative effects in large quantities. And and then why, again, the kind of confounding variables here when it comes to blocking the production of uric acid, where it's not as simple as you're just reducing uric acid production. There's a really important component here having to do with xanthine oxidase. That's a huge confounding variable when it comes to that argument. So when we look at uric acid, the first question is basically, is it just this toxic agent? Does injecting uric acid create damage? Does having higher levels just create damage? Is it just this molecule that is a byproduct of a toxic metabolic state that's just going to wreak havoc? And in short, the answer seems to be mostly no. And it seems to be extremely protective in certain contexts, again, when it's not at extraordinarily high levels for, in the serum for long periods of time. And they've shown this in some pretty unique situations where they show that basically uric acid is able to protect cells from all sorts of damaging interventions. And it's also particularly protective against ischemic brain injury in neurons. And that was one that a study that they did in vivo, where they were adding in uric acid and found it to be protective. They found it to be protective in ischemic stroke, decreasing TLR4, NF-kappa B, like just some of the primary drivers of inflammation tend to be opposed by uric acid. So it has a lot of, and this is why it's considered to be an antioxidant widely, it's because it has a lot of these protective effects. And there's an interesting study I want to discuss that's looking at uric acid as a potential reaction to atherosclerosis and looking at it in terms of heart disease. And this is an interesting argument because it's very parallel to the alternative spheres argument for cholesterol and heart disease. So what's often pointed to is that you see high cholesterol in states of cardiovascular damage and disease. And that association there is not actually caused by the cholesterol, but rather the cholesterol is there as a protective factor. And people always say, or like kind of a common analogy is that you don't blame a fireman or you don't blame the fireman for a fire, right? The fire is already there and they're there to clean it up. And so there's a very parallel argument for uric acid in a lot of these contexts. I'm going to share a quote here from a study that's making that argument. All right, so this is a study titled Uric Acid and Serum Antioxidant Capacity, a Reaction to Atherosclerosis. And so what they're arguing here is basically that elevated serum uric acid in atherosclerosis is a compensatory mechanism. It's compensating for the oxidative damage that's going on in atherosclerosis and aging. And this part is added by me that this is very similar to the cholesterol LDL argument. And so they state that increased uric acid may be a compensatory mechanism trying to counteract oxidative stress as proposed by Ames and Hochstein's groups. After showing that uric acid is an effective antioxidant, Ames et al. Hypothesized that uric acid may be an evolutionary antioxidant substitute for the loss of ability to synthesize a sorbate in higher primates. This is something that we'll be getting to in a little bit in terms of the whole uricase situation and primates. But then they go on to say that in humans, uric acid exists in blood at concentration close to maximum solubility, solubility being the point where after that point it would precipitate out and create uric acid crystals, which is what happens in gout. So just saying that we maintain very high uric acid levels. And again, this is going to be relevant later on. Ames et al. Suggested that these high levels may be the result of the evolution of effective protective mechanisms against oxygen radicals, and that this may partly explain the marked increase in lifespan and the decrease in cancer rates in the evolution from prosimians to modern humans. Although plasma uric acid is not as effective as plasma sorbate in preventing the initiation of lipid peroxidation, it does lower the rate at which lipid peroxidation occurs. Moreover, uric acid stabilizes a sorbate in serum, largely due to its iron chelation properties. So a couple of really key important points here, basically showing that uric acid is protective and slows lipid peroxidation, protective against oxidative stress, helps to stabilize the sorbate, being vitamin C, by chelating iron. So these are all particularly noteworthy benefits, especially when it comes to what's going on in atherosclerosis. And they'll also certainly be coming into play in a little bit when we talk about why it might be that humans have uricase. And maybe it's not just because we want to get really fat, but instead, maybe it's actually protective. And as they allude to here, maybe it led to decreased cancer rates and increased lifespan and helped us cope with lower serum sorbate, which we'll get to as well.
Yeah, there's an element. So there's a series of hypotheses around why humans lost the ability to synthesize vitamin C directly. And there's a whole interesting kind of cascade where you see that when humans and apes lost the ability to synthesize vitamin C, they actually increased their serum uric acid overall. And they talk about, the antioxidant hypothesis is one of the main ones. But they also talk about like the creation of vitamin C actually generates ROS through one of the enzymes. And so it has like a net, it has a net neutral effect as far as dealing with oxidative stress to a large extent. Which is quite interesting. So there's a hypothesis that losing the sorbate was kind of as a protective mechanism to limit some of the ROS, and then also in the liver specifically, and then the uric acid was, as they discuss here, a mechanism to pick up that lack of antioxidation. They also talk about, so in the loss of the production of ascorbic acid, they're saying because fruit primates at this period of time had such access to large amount of fruits that it was likely that they lost the ability to synthesize vitamin C or ascorbic acid because they were getting large amounts in their diet, and getting it from the diet was actually a better choice overall because the production of vitamin C in the liver created ROS. So some interesting hypothesis around that, but there does seem to be this relationship with a loss of uric acid or uricase, and then also the loss of the enzyme, the final enzyme that catalyzes the step of the conversion of, I think it's UDP glucose to ascorbic acid, if I remember correctly. So that's like an entirely different podcast, but just interesting note to put in there.
Yeah. Well, the whole uricase evolutionary side of things is an important piece of the argument. So we will get there and talk about it in more detail for sure.
Yeah.
So were there any like quotes or anything that you wanted to share regarding like the uric acid being protective, or we can just, I was thinking we'll just cite those studies in the notes.
Yeah, we can just cite the studies. It's essentially the same stuff. They're just saying, so they're talking about the alternative hypothesis that elevated serum uric acid represents a physiological and protective response to oxidative stress that characterizes many vascular diseases. They say in a rat model of cerebral ischemia, brain uric acid concentrations increased, and in a transient ischemic model, infusion of uric acid led to a reduction of infarct volume and improved behavioral outcome. So they had rats, they gave them an infusion of, it led to an infarct, so a stroke, so piece of brain tissue that died essentially. And then when they perfused this uric acid, it was actually protective and improved the outcomes. And then essentially they looked at models of rats and traumatic brain injuries and multiple sclerosis, and they found uric acid was found to reduce the formation of peroxynitrite radicals. So those are free radicals peroxynitrite radicals are actually some of the worst. So that's an interaction of reactive oxygen species with nitric oxide, and uric acid being protective in those situations. And then there's some talk about association studies or there's actually, these are human studies where uric acid administration has been shown to increase serum antioxidant capacity. So just interesting pieces like that. That again, there's the context of uric acid is important because it does seem like in high levels at with high amounts of intracellular uric acid, there is actually oxidative stress created by the uric acid. But in an extracellular environment, like in your serum or whatnot, the uric acid does have an antioxidant effect. So part of this argument does belay or rely on what amounts are we talking about and what context are we talking about with the amounts of uric acid that are actually present. But it's not just like a pure toxin. It's not it's not like endotoxin, or it's not like even ROS. There's question about some of the benefits and signaling and whatnot, but it's not like just a purely negative compound that we want to just hammer down into the ground and it's causing all these problems. It's more of a marker or an indicator, and they talk about this in the studies, that possibly indicating other problems going on. And I guess we'll talk about some of the negative effects or some of the confounding factors in a moment.
Yeah, exactly. So they acknowledge, and this is part of why we weren't kind of sharing all the, like going into deep on these studies, is because this is acknowledged that uric acid does have some protective effects, but then they say that overall it's negative. And one of the large pieces of evidence that they point to is that if you inhibit the production of uric acid, you see benefits. So obviously, uric acid itself must be a problem. And so there's a huge confounding variable here that I think we might as well get to now, which has to do with the production of uric acid. And so we talked before about the pathway from fructose to uric acid. And so at the end there's a couple of different enzymes that can lead to the production of uric acid. And so I'm going to pull this graphic up in a moment. There's a couple of graphics that kind of show the differences here. But the important point is that basically these substances that they're using to block uric acid production, which are the purinols, don't just block uric acid production. They do it in a particular way, which is that they block xanthine oxidase. And just because that is beneficial doesn't mean that the uric acid is harmful, is causing the harm, but rather the xanthine oxidase itself seems to be a pretty major problem and is largely responsible for producing the oxidative stress that they're blaming on uric acid. And that's because in the process of producing uric acid, it creates reactive oxygen species, including superoxide, and then that leads to further like oxidative stress agents and reactive oxygen species like peroxynitrate. So I'm going to pull up a graph here showing that whole process, or a graphic. So this is showing the whole pathway. In a second, we'll zoom in on just the last part. But so we talked about, again, when you have the fructose coming in, it's supposed, in certain contexts, depleting the ATP, converting it to ADP. We've got this whole pathway. And then we get to the hypoxanthine, and this is 2 steps before uric acid. And so the enzyme that converts hypoxanthine to xanthine and then xanthine to uric acid is the same. There's the xanthine oxidase, which is the XO on the right, and there's xanthine dehydrogenase, and that's the XDH on the left. And you can see here that they're doing this through 2 different ways. One of them, the xanthine oxidase, is using oxygen and then producing a free radical, superoxide. And on the other side with the xanthine dehydrogenase, it's using NAD plus and converting it to NADH. And so this happens twice when you go hypoxanthine to xanthine and then xanthine to uric acid. So I'm going to pull this up in a more zoomed in one so we can just focus on this area. All right, so here we can see on the top, we've got the xanthine dehydrogenase converting hypoxanthine to xanthine using NAD, producing NADH, and then the next step, same thing to uric acid. And on the bottom, we've got the xanthine oxidase doing the same thing, but producing, oxidative stress agents in the process. And yeah, so I don't know if there's anything you want to add here, but what I will say real quick, again, is that when they're adding the purinols to reduce the production of uric acid, they're not blocking xanthine dehydrogenase. They're blocking xanthine oxidase. So they're blocking the enzyme that produces free radicals, produces oxidative stress agents in this situation. So it's not, when you're adding the purinols, it's not that you're just getting less uric acid, it's that you're blocking the production of reactive oxygen species in the process. And we'll talk in a second about what regulates these 2 enzymes and what causes what causes your body to use xanthine dehydrogenase more than xanthine oxidase and vice versa, because that's really important and goes directly in line with everything else that we're saying. So we'll get to that in a second.
Yeah, so that's essentially where I was going to go, is that, again, this is a contextual situation where the context is really important, because in one context you have a situation where, first of all, you have a situation that's not super pathologic, that allows xanthine dehydrogenase here to just create NADH, which is not necessarily a toxic compound.
Not at all. I mean, it's a normal, like if you're running through glycolysis, Krebs cycle, you're producing a lot of NADH. It's used to then produce ATP at the electron transport chain. Super important.
Yeah, and then on the flip side, in a more pathologic situation, you have an enzyme, or the same enzyme, but just it's been altered, and now it's xanthine oxidase, and it takes this hypoxanthine and takes oxygen, and it produces xanthine, and then you have a superoxide and hydrogen peroxide radicals. So you have two pretty potently toxic or potentially toxic compounds and damaging compounds inside the cell that are created by this enzyme. And the switch in this situation, I'm going to read a quote here. So basically what they're saying is an in vivo xanthine oxoreductase, which is the XOR, exists in two interchangeable forms, with about 80% existing as xanthine dehydrogenase and the remainder as xanthine oxidase. In both forms, xanthine oxoreductase catalyzes the conversion of both hypoxanthine to xanthine and of xanthine to uric acid, and under normal conditions uses NADH as a cofactor. So that's what you're seeing. That's what you're just seeing in the previous graph. But however, in ischemic or hypoxic tissues, large quantities of hypoxanthine accumulate. Why does that happen? That happens because you have like a depletion of ATP, and so you have a buildup of that ADP, and then you also have a buildup of the AMP, and then essentially produces adenosine and inosine that move down that pathway.
Mm-hmm.
And so the availability of that NADH declines. The ratio of the oxidase and dehydrogenase forms of xanthine oxoreductase may be reversed. So essentially, you're getting more xanthine oxidase. As a result of these changes, when oxygen is restored to the cell, the xanthine oxidase catalysis of xanthine and hypoxanthine is altered, with NAD plus and dioxygen, or oxygen, now used as cofactors, resulting in the production of hydrogen peroxide and superoxide anions. Thus, during reperfusion, there may be extensive production of ROS. So in situations of hypoxia or ischemia or impaired metabolic states, you essentially, so basically you have this large amount of the ATP breakdown, etc. You get a conversion of the xanthine dehydrogenase to the xanthine oxidase. So overall, when we're looking at these studies with uric acid, and they're taking allopurinol, which is essentially a molecule that binds into the xanthine oxidase pocket where it would interact with hypoxanthine or xanthine, and it blocks the hypoxanthine and xanthine from basically being able to be converted into that uric acid. But so yes, you have lower uric acid in this situation, but you also get lower superoxide, and you also get lower hydrogen peroxide. So when you're looking at these studies, it's kind of hard to parse out, am I getting this beneficial effect from the purinols, the purinol drugs like allopurinol, oxypurinol, because I'm lowering the uric acid directly? Or am I getting this beneficial effect because I'm blocking xanthine oxidase, which produces these toxic ROS compounds, especially in like impaired or damaged metabolic states? Now, this creates a huge confounding factor, because a lot of times the metabolic syndrome that we see is characterized by this, is essentially an energy metabolism problem. So you're having these hyperexcitatory states, you're having this backup of metabolism leading to this depletion of ATP inside the cell, and then possibly increasing the amount of cytosolic calcium 2+, and having the calcium signaling, etc. So you may be increasing that xanthine oxidase signaling overall, and then having overall oxidative stress from that, on top of having the oxidative stress from the impaired metabolism, and then blocking some of the oxidative stress from the purinol drugs, is having a helpful effect regardless of whether uric acid is decreased or not. So it's hard to parse some of these things out. So yeah, I don't know where there is more to discuss, because there is issues with uric acid in high concentrations as well. But overall, it doesn't, like this, looking at these studies and saying, oh look, we blocked xanthine oxidase with this purinol drug, so therefore uric acid must be bad, is kind of a stretch.
Yeah, you definitely can't. I would essentially say you cannot use that as evidence for uric acid to be harmful.
Exactly.
Because of this huge confounding variable. And so here, as you were kind of describing, they're talking about NADH, but it's really NAD that is being used, in the xanthine dehydrogenase situation to catalyze the reaction and to produce uric acid. And, again, that NAD is going to be depleted when you have a low NAD to NADH ratio. We talk about this all the time as the hallmark of an inhibited, inefficient energy production, whether it's due to fat oxidation or anything blocking the process on from there. We talk about this all the time. So that is just directly at play here. So you could even argue that even if you had excess fructose coming in all at once, you're producing uric acid, but you're just doing it using the xanthine dehydrogenase, it's not going to really be causing much of an issue. Now, we'll talk about, again, extraordinarily high levels of uric acid being an issue, but that's, again, it's a stretch to even argue that fructose is going to drive that, as we've described. So they're showing that here. Again, that NAD side is what they're kind of focusing, and they're showing this in the context of ischemia and hypoxia. And there's another study I'm going to share here that's describing the calcium side that can also affect this process. So the second factor here that is another major, that has a major impact on whether it's going to be xanthine dehydrogenase or xanthine oxidase that is causing the conversion to uric acid is intracellular calcium. And so they state here that increased cellular calcium is harmful. One of its important consequences being the activation of a calcium-dependent protease, which cleaves xanthine dehydrogenase to xanthine oxidase. During reperfusion, molecular oxygen is reintroduced into the tissue where it reacts with hypoxanthine and xanthine oxidase to produce a burst of oxygen-free radicals, namely superoxide anions and hydrogen peroxide. So again, they're identifying here the other major factor that's going to shift from xanthine dehydrogenase to xanthine oxidase being increased intracellular calcium. And as we've discussed, that is the result of an energy deficit and energy failure. And so, again, coming back to this point that it's really a inhibition of proper energy production, mitochondrial respiration. That is the problem that is driving oxidative stress. It is not fructose. Fructose doesn't cause those things. And and this is again pointing to the situation with allopurinol not being effective evidence for uric acid itself being the issue.
Yeah. So just the importance of context overall.
Yeah, absolutely. And then the other thing I did want to mention is the AMPK versus AMP deaminase situation. So they talk about how this whole process will inhibit AMPK in favor of AMP deaminase. But this is, again, only something that's going to happen when there's excessive phosphate depletion. So if we go back to that original diagram, the original graphic, so this is actually the second graphic showing the fructose to uric acid pathway, and you have that ATP to ADP, and that continuing on. And so they show AMP deaminase here, and this is only happening when there is this excessive phosphate depletion and you can't replenish that ATP. And again, we discussed that it's pretty hard to create that state from fructose. So the situation where you're going to have this active AMP deaminase and inactive AMP kinase is, again, it relies on all the same context that we've been putting forth this entire time.
Yeah. So in a normal, when you say from fructose, you say normal consumption patterns that even the average American would follow. You wouldn't see this type of problem. And I think I'm trying to look here and see. So a normal consumption pattern established in the US, I'm going to just highlight it here for you guys. It says it is important to note that fructose intake varies between individuals based on their daily consumption patterns. Through a 2008 US survey in 21,483 children and adults, it was found that the mean intake of fructose was 9.7% of total energy intake, and that 95 of these sampled individuals consumed less than 19.5% of fructose as part of their total daily energy intake. Therefore, in discussion, we assume fructose intake to be excessive if its pure intake amount is larger than 20% of daily energy. So on a 2,000 calorie diet, just so to put this into perspective for people, that would be 194 calories worth of fructose. Divide that by 4. So that'd be about 48 grams of fructose per day. And that wouldn't be in one bolus.
Wait, it said 20% of calories from fructose, right?
No, it said 9.7%. It was found that the mean intake was 9.7% of total energy intake. And
Gotcha,
so it's 95% of people consume less than 19.5% of fructose.
Okay. So you're going based on the mean.
Yeah. So the mean was about 48 grams of fructose a day. And keep in mind, that's probably divided by 3 meals or more. So you're talking about 16 grams of fructose per meal, which is a far cry from a 75-gram dose that you would take orally, or 219 extra grams per day on top of the 11% of calories, which would probably be around 50% or 50 grams per day. So you're like, the dosages that we're talking here, again, it's out of control. Even the injection, even injecting the 25 grams, you're injecting 50% of your fructose into the vein in one shot. It just doesn't, especially considering, as we talked about, like the actual general fructose concentration in the blood would never have even gotten close to achieving that. Even glucose concentrations for most people should never even get close to achieving that.
Yeah, 100%. All right, we're going to wrap this episode up there and pick back up in part 2, the final part of this series, where we'll be discussing whether we should be avoiding fructose-containing foods due to their potential to increase uric acid, whether the fact that we lack uricase means that we should not be consuming fructose-containing foods. We'll also be talking about the role of endotoxin and gut health in uric acid production and gout. We'll be talking about which fructose sources are ideal and how to adjust our fructose intake if we're dealing with insulin resistance or non-alcoholic fatty liver disease or gout. If you did enjoy today's episode, please leave a like or comment if you're watching on YouTube. And if you're listening elsewhere, please leave a review or 5-star rating on iTunes. All of those things really do a lot to help support the podcast and are very much appreciated. To check out the show notes for today's episode, you can head over to jfeldmanwellness.com/podcast, where you can take a look at the studies and articles and anything else that we referenced throughout today's episode. And if you are dealing with any low energy symptoms, whether those are related to some of the conditions we've been discussing today in terms of metabolic syndrome and insulin resistance, non-alcoholic fatty liver disease, or gout, or if these are other low energy symptoms like chronic cravings and hunger, low energy and fatigue, chronic joint pain or weight gain, or digestive symptoms like bloating, or if you're dealing with brain fog or poor sleep or hormonal imbalances, then head over to jfeldmanwellness.com/energy, where you can sign up for a free energy balance mini course, where I'll explain how these different symptoms and conditions are really caused by lack of energy. And I'll also walk you through the main things that you can do from a diet and lifestyle perspective to maximize your cellular energy and resolve these symptoms and conditions. So to sign up for that free energy balance mini course, you can head over to jfeldmanwellness.com/energy. And with that, I'll see you in the next episode.